Yeah, welcome to Numerical Methods for Mathematical Finance. And today I like to continue our session on random number generation. So actually we are here in this session on random number generation, but maybe let's start with a small recap, because we are doing the random number generation with a special application in mind, and that was our Monte Carlo method. So we started this journey by first observing that we can approximate here the expectation. So we were considering here the expectation of a random variable x, and we can approximate this expectation by looking at a sequence of IID random variables that have the same distribution than x. So it is the expectation of x1 or xi that we are approximating. And we can approximate this expectation by just taking here the running average of these IID random variables. So the disappointing aspect in this approximation was that here our error bound, so we had a nice error bound here, this was telling us as we increase n, the error becomes smaller as 1 divided by square root of n. So this result on this error bound was here only in probability. So we could say that we are in this bound with a certain probability. We can make the probability quite large. Then the bound becomes a bit poorer, but we cannot make it one. Yeah, we discovered that this method had some nice properties, especially when we looked at an application, and our application was the Monte Carlo integral. So we are just now considering a special sequence. So the sequence were now uniform distributed here on the unit cube 0, 1 to the power of d. And then we just applied a function such that we get again here a sequence of IID random variables, f of xi now. And since these guys, the xi are now uniform, this is an approximation of the expectation, which is just the integral f of x dx. So we can see it as an integration method. And then, of course, we can repeat our convergence result to state that we have here a certain error bound for the approximation of this integral. And that was the Monte Carlo integral that is now approximating this integral. We then introduced here in our section on random number generation a property for the sequence. Well, okay, why random number? If we go back here, this is formulated in terms of random variables, but when we apply it in a computer, we are just generate drawings. So we are looking at a single event. So the thing is that we are plugging in here a single event omega such that the xi of omega becomes a little xi, a sequence of random numbers. And of course, that looked a little bit as if it is not admissible, because the whole thing, again, only holds in probability, and it wasn't clear if it holds on this omega. So omega could be a null set, so it could be completely off. One other remark, note that the dimension d, so this here was already integration in d dimension, the dimension d was not appearing here in this error bound, and we had also a nice intuition why this was the case, because drawing a random vector means drawing random components. So we add something new to every component. So we have actually an improvement in every dimension. So we clearly understood why the method had this powerful advantage. And moving then here to our chapter on random number generation, we were introducing a concept that was exploring this property of, say, filling the space in a certain sense. Yeah, we were exploring this for general sequences. So we introduced the concept of the discrepancy. And with the concept of the discrepancy, we could actually derive a similar error bound, but now without the probability. So we had here again our Monte Carlo integral approximating the d-dimensional integral. And now the nice thing was that our error bound was given by a constant depending on the function, the variation of the function, multiplied with the discrepancy of the sequence. And somehow the discrepancy is just the intuition. Are there spaces where I have very few points, or are there spaces where I have clusters where I have too many points? Yeah? So it measures if the sequence is filling the space evenly. So this clearly motivates that I would like to have here a sequence of random numbers that has small discrepancy. And that was where we stopped last time. And so now I like to continue and create sequences that have low discrepancy. And now using the Monte Carlo integral, which is just this average of f of xi, with a sequence xi, using the Monte Carlo integral with such a sequence, which is constructed in a special way. So it is not a sequence of random numbers. It is not a random drawing. It's constructing in a special way. This method is then called quasi-random number generation. This is the name for the sequence. So it's called Quasi-Monte Carlo. So the other sequences were called pseudo random numbers, because the computer just creates an algorithm that it looks random, but maybe it's not truly random. So let's start by looking at this in one dimension. So if we do not have the special knowledge about the function f, our error estimate, so the Cox-Malavka inequality, suggests that we should look for a sequence xi that has low discrepancy. And we already made this experiment when we were looking here at the Monte Carlo integral. So 1 divided by n, take the sum of f of xi, so just function evaluation. When we compare it, for example, to the Simpson's rule or the true Monte Carlo with a random number sequence, we also looked at the case where we used a very special structured sequence. And that sequence was here, xi is just the equidistant partitioning of my interval from 0 to 1. So I'm looking here at an integral from 0 to 1. Of course, you can just transform the domain with the rule of substitution. And we saw that this sequence, I divided by n, I running from 0 to n minus 1, for example, this had discrepancy 1 divided by n. And that guy was almost optimal. Well, a short remark. We also saw that there was a guy which was a little bit better. It was I plus 1/2 divided by n. So that is our xi, I from 0 to n minus 1. So I just take the center points. So the distance, the maximal distance I see then in this expression that defines the discrepancy is 1/2 times 1 divided by n. So we get the d star for this sequence is 1 divided by 2n, and that was the optimal guy. Well, but this sequence is not what I want to create here. Yeah, so it is not the low discrepancy sequence that I'm looking for, because it has a disadvantage. Whenever I change the number of sample points n, I have to completely recreate the sequence, at least for many cases. Yeah, if you just double the number of n, you can reuse the previous points maybe. But if you just increase, for example, n by just 1 point, so by just one, then you have to recreate the whole sequence, because it's just completely new points. So this discretization loses a very special property of the Monte Carlo method, and a property that came from the original motivation that we use a sequence of random variables, random numbers. Because if we have these IID random variables, the sequence of IID random variables, then every new one is completely independent from the previous one. So I can just enlarge the sequence by adding more and more points. And this is now what we would like to see here. So the idea of a low discrepancy sequence is to generate an infinite sequence such that every subsequence, so the elements from 1 to m, has low discrepancy. Okay, so I'm looking for xi. So I'm a programmer, let's count from 0. Okay, an infinite sequence such that d star is small, for all m. Okay, so it should become smaller and smaller, maybe in a certain way, such that I get a convergence result using my Koxma-Lafka inequality. Yeah? So if I increase here the number n, I should have some convergence. Okay, so I would like to save this property from the Monte Carlo method, that I can increase the sequence. Here is a very nice, prominent example. So a simple example for such a low discrepancy sequence here in 1 dimension is the van der Corput sequence. Okay, so there is a parameter b. B is an integer larger than 1. This is called the base. And then the van der Corput sequence xi. So this is a sequence in 0, 1 with base b, is defined by xi is the sum j from 1 to infinity alpha ij. So every xi has a sequence of coefficients here, alpha ij, times b to the power of minus j. Okay, and how are the alpha ij defined? So the alpha ij, so these coefficients, are now integers between 0 and b minus 1, such that the index I is represented by the infinite sum j from 1 to infinity, alpha ij times b to the power of j minus 1. Okay, that looks at first maybe a little bit complicated, but actually it's a really simple and easy idea. So first note that these infinite sums here are actually finite sums. So for a certain index k, this coefficient alpha ij is 0 if j is larger or equal than k. Of course, the k depends on the I. Well, So for a given index, yeah, I just need a finite number of these coefficients, yeah, because the b to the power of j becomes larger and larger. Then, of course, this here is also a finite sum. And I can calculate the x. Well, what's the alpha ij? You see that this here is b to the power of, okay, it's j minus 1, 0. So this is 1. Then b to the power of 1. So this is b. Then b to the power of 2. Yeah. So these are just like in a binary or ternary or whatever digit, a b-adic representation of the number I. So then you just use these coefficients in front of the factors, which are now 1 divided by b to the power of j. J now running from 1 to infinity. So if, for example, b is equal to 2, then this here is just the binary representation of the index. So binary means the alpha ij is in the set 0 or 1. Of the index I. So I'm representing the index I in binary form. So for example, a 3, yeah, is just a 2 plus a 1. Yeah, so it is a 1, 1. Then you use these coefficients 1, 1 and sum the fractions, so the binary fractions. So j equals 1 was the coefficient that was in front of the 1. It's now the coefficient that is in front of the 1/2. J equals 2 was the coefficient that was in front of the 2, and it's now the coefficient that is in front of 1/4. So these numbers become smaller and smaller. Okay, so now if you look at the example b equals 2, it's quite easy to see what's happening here. So let's consider here the case base b equals 2. That means I'm now representing the index I in binary form. So the coefficient in front of the 1 or the 2, or then the next digit is the 4. Of course, if you then represent the 1, it's 1 times 1. The 2, it's 1 times 2 plus 0 times 1, it's 1, 0. The 3, it's 1 times 2, 1 times plus 1 times 1, it's 1, 1. The 4 is 1, 0, 0. Okay, so you represent the index in this form. And then you take the corresponding fractions. So it's 1 divided by 2 to the power of j. So these are now the corresponding positions 1/2, 1/4, 1/8. And you just translate the coefficients alpha ij from the binary representation of the index to the fractions. Yeah? So if you have here a 1, 0, 0, you will get on the other side the same sequence from the alpha ij, a 1, 0, 0. So in that case, the xi for I equals 4, so the fourth number in my sequence, is 1/8 plus 0 times 1/4 plus 0 times 1/2 is 1/8. So how is now this sequence populating my interval from 0 to 1? So the first guy is 1/2, my base to the power of 1, so it's 1/2. Then I move to the next digit in my binary representation. So I'm looking now at all the fractions that have a 1 divided by 4 inside. So the first one is the pure one, 1 divided by 4. So it's that guy. So that guy goes here. Okay, then I add the other digits. So I add a 1 over 2. So it's 1 divided by b to the power of 2 plus 1 divided by b to the power of 1. So it is 3 over 4. So I'm populating that guy. Okay, so and now you see that you are just halving every interval. So since now I have intervals of size 1 over 4, so that interval has a size 1 over 4, yeah, and I have 4 times this interval. The next refinement level is 1 divided by 8. But now how do you distribute these points? Yeah, it's not that you go from left to right. You try to fill the space a little bit more evenly. So actually the funny thing is that your first one, the 1 over 8, is just the one where your binary digit here is 1 and all the others are 0. So that one clearly goes here. But then the next ones are just by repeating the previous points with this shift of 1 over 8. So it is 1 over 4 plus this shift, 1 over 2 plus this shift, 3 over 4 plus this shift, and in the order that we had previously. That's just because in the binary digits, it flipped the bit here. Yeah. So you see here I'm adding the additional point. Yeah. The higher bit is flipped to a 1, and then the lower bits are just repeating the sequence. Yeah. So that's why I'm now taking here the 1 divided by 8, and I'm just adding here this part to that part. So I'm taking here the 1 divided by 8, and I'm just adding this part to create here the new numbers. Yeah, so it is 1/2 plus 1 over 8. It's 5 over 8. It is 1/2 1 over 4 divided by 1 over 8. It's 3 over 8. And then it's 3 over 4 plus 1 over 8 is 7 over 8. So the next guy is the 5 over 8, and it is then going here. And then the next guy is the 3 over 8. Okay, that guy is going here. And the last one, the 7 over 8, which is going here. Okay, that's a very nice algorithm. Yeah, and you see, you are reaching always at a certain point a level where you have this nice equipartitioning of this line from 0 to 1, and in between, yeah, you are filling the space also in a way that you are not always looking at the same side. Yeah, so I'm not going from left to right. Yeah, I'm distributing this in a nice way. Yeah, and of course the next guy would be the 1 divided by 16, and then you know the next one would be here. Okay, and it went on. Yeah, so that's the Van der Corput sequence. So the first 7 elements here of this sequence with base 2. That is the exercise that we just did. Yeah, 1/2, 1 over 4, 3 over 4, 1 over 8, 5 over 8, 3 over 8, 7 over 8. Okay, you can also do this with a different base. Yeah, if you take base 10, then you just count your digits from 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so you count here the digits in base 10. And then the next refinement is 10 to the power of 2, which is 1 divided by 100. yeah, 0.01, and you then repeat this by just adding again the sequence that we had before. Yeah? So it's then the same principle. It's 0. Sorry. It's 0.11, 0.21, 0.31, and so on. Yeah? That would be the sequence in base 10. So the one-dimensional low discrepancy sequences, they can be constructed to have always a discrepancy that is order log n divided by n. So this sequence, you can prove that it also has this order. And more important, the van der Corput sequence has some properties which are now very nice, yeah, in a computer implementation. So first, we reached the goal that we have an infinite low discrepancy sequence, so we can improve the accuracy of our Monte Carlo integration by just adding new valuation points, reusing the previous one. Yeah. And you see log n divided by n is better than 1 divided by square root of n. But of course, the sequence is not as good if we just take the best partitioning for the number n. But we have here now a sequence that we can continue, so we can improve the accuracy. There is another nice property, which we maybe not looked at during the lecture. The index has an explicit formula for the i's element, so for xi. So we have an explicit formula here for the i's element. Yeah, if you know the index I, you can calculate these coefficients. We will see that this is quite easy. And then we can, from the coefficient, calculate the x. So it's not like in our linear concurrential generator that the next element is a function of the previous element. So we have something like a random access thing here. So we can generate the sequence at a point in the future without having the need to generate all the previous points. So this property that we can generate the sequence for a given subinterval of the index set, so we can start the sequence here with an offset to the index. This is really useful if you would like to implement now the integration in parallel. So if you like to parallelize the integration algorithm, you could now take one sequence that runs from 1 to 1000, and the next sequence runs from 1001 to 2000, and the next sequence runs from 2001 to 3000. So you can create these batches. And since each one can just take its starting value and generate the sequence, yeah, he doesn't need to do the work before. You can just create these independent workers and distribute the load across different machines, across different processors, so you can parallelize this. So this feature is then sometimes also called skip ahead. So you can skip a few elements in the sequence very easily. And there are formulas for linear concurrential generators where you can also derive such a property. Yeah? So if you would like to start the sequence at a later point. But here it's really easy because we have an explicit formula. Yeah, let's try to implement this and maybe use it in our Monte Carlo integration. So first coding session for today, I would like to create a class Corput Sequence that implements this sequence. And maybe I would like to do it a bit nicer. I would like to define an interface, which I call random number generator 1D, where we can collect our random number generators. Previously, I didn't define a separate interface. We were just using the double supplier in our Monte Carlo integration algorithm. But once we have done this, we can maybe also implement the double supplier and then use this sequence in our Monte Carlo integrator. Yeah? So we can go back to the session where we already implemented an integration rule that just needs the sequence as an input. So let's do this a little bit together. Yeah? So I will create here a new, well, first let's create a new interface. The package name should be here, yeah, numerical methods lecture random numbers, and my interface, let's call it random number generator 1D. Yeah? So because we will move to higher dimensions a bit later. So this interface is just that I have a method that returns the next random number. Okay, so I have this definition here of my random number sequence. So let's create the new class. That is my Corput Sequence, and it should implement my random number generator 1D interface. That one. Okay, so maybe I would like to name this get next double. Yeah. So I see that it is a one-dimensional thing here. Okay. So I just have renamed this. So I need to implement here the Corput sequence. Well, my Corput sequence gives me the number for a certain base B. In my example, that was 2. I was using base 2 in the example, and an index. Let's just implement this formula as a static method. So I would like to have a certain base, and I have a certain index in my sequence. Okay, so how does this work now? Let's go back to the slides. So first little remark, you see that here the coefficients and the indices, they start at 1. Okay, so maybe this is missing here, yeah, but here my I starts in 1, 2, 3, and so on, yeah, as we had here in my example, I from 1, 2, 3, and so on. So here in the definition, the I starts in 1, but I'm a programmer. My indices start counting in 0. So the first thing is that when the user here provides an index, the first number he provides is the index 0, but my index for the Corput sequence is in the formula 1. Yeah, so let's just shift the index. Okay. Yeah, then you see that we have here the base, yeah, and we just increase here always the base, yeah, 2, 4, 8, yeah, always multiply with 2. But here we always divide by the base, so it's 1/2, 1/4. So I have here a factor, and the first factor is 1 divided by b. Yeah, I start with j equals 1. The first factor here is 1 divided by b. Let's define this factor or fractional part. So the fraction I start with is 1 divided by base. This is the fraction I start with. I would like to create now the number xi that belongs to this index. It's a sum. Yeah? So let's start with 0 and sum all the summons. So while I would like to sum this, which is the first guy. So the first guy is AI1, and AI1 is the coefficient in front of b to the power of 0. Because of the 1 minus 1 is 0. So it's the coefficient in front of the 1. So actually, when is this coefficient different from 0? It's the question if the index is divisible by b. If you look here at our example, so 1 divided by 2 has remainder 1. So it's the remainder of the division. 2 divided by 2 has remainder 0. 3 divided by 2 is 1, remainder 1. 4 divided by 2 is 2, remainder 0. So you see actually that this coefficient here is the remainder of the division by b. So the coefficient bi1 is the remainder of the division of the index I with b. Let's just calculate that coefficient. So it's the remainder of the division divide the index by base. Okay, and then that coefficient is multiplied with my fraction. So I have already defined here the first fraction. So it is x plus the coefficient I need to get some concentration today. Okay, so it's x plus the coefficient multiplied with the fraction. Okay, so now I have to check if the index can be divided by, okay, that was division by 2, the next one is division by 4, and so on. So I have to check all these guys. But in that of doing this, I can just update my index. Yeah. So my index is now my new index divided by 2, which will shift all the bits, yeah, by 1 position. Or here, if base is not equal to 2, but something else, it is index divided by base. That's a division without the remainder, which will throw away the remainder and shift everything to the next position. And of course, the next fraction is 1 divided by base to the power of 2. So I have also to update the fraction. So the fraction is the previous fraction divided by base. So this makes here the index smaller and smaller. And the last index is then 1. So I just check if this has here a remainder. If this has a remainder, then I have a coefficient. If the index would be 2, and the base would be 2, it has no remainder. And then the last index here is 1. So I just check if the index is larger than 1, then I continue that. Okay, so I believe it is correct. Let's try. So let's return now the x. Maybe I have to add here a return value. Yeah, and maybe we also add here a small test program that maybe prints the first 20 van der Corput numbers. So let's run here I from 0 to say 20, yeah, or 90 I plus plus, and let's print out the first van der Corput numbers for base 2 and index I. So let's have a look if this looks correct. Oh, I did something wrong, right? Yeah, sorry, the last index is 1. Okay, that's a mistake here. Okay, sorry, there's a mistake. The last index is 1. So this is as long as the index is larger than 0. So once I have then reached here the 0, then I stop. Okay, so let's try that. Okay, so that looks a bit familiar. Okay, that looks like we have it here. Yeah, 1/2, 1/4. So I start with 1/2. So that's index 1. Okay, maybe we can try that. I enter here with index 1, actually 0. Yeah, then I move it here to a 1. My base is 1/2. The index is not yet 0, so I enter the loop. 1 divided by 2 has a remainder. So it gets a coefficient of 1 in the fraction, so I get the 1/2. I make the index 1. I divide it by 2. Yeah, this division will give me then a 0. You know, it is 0.5, but the index is an integer. It will get a 0, and then the loop will stop. So if I then enter with, say, an index of 2, I of course enter here with an index of 1. So the next one is the index of 1. I will move that index to a 2. The fraction is 1/2. The index 2 is larger than 0. 2 divided by 2 has remainder 0, so there will be no 1/2 here added. The index will be moved 1 digit smaller. Yeah, the index becomes a 1. So I enter again here. The index is larger than 0. 1 divided by 2 has a remainder. It's a coefficient 1, but the fraction had been updated to 1 divided by 4, so I will get the 1 divided by 4. So the next guy has then the index 2, which will move to a 3. Yeah, and a 3, of course, I get 2 remainders. I get a remainder in the division by 2. So I get that guy here, and I then get, if I move the 3 to a 1, I divide by 2, then I will get another remainder. So I will get 1/2 divided plus 1/4, which is the 3/4, and so on. Okay, so maybe we can also test here the base 10. And you can test now all other bases. Yeah, and you see that also we have here some rounding errors which come from, we are doing a sum. Now you already know summation can create these kind of rounding errors. But apart from that, it's like in the script, I'm running from 1 to 9, and then I increment the next position to 1 divided by 100 and run again from 1 to 9. You can also check, maybe also nice is base 3. Okay, it's 1/3 2 divided by 3, and then 1 divided by 9, 3 times 3, and then it's this guy plus the 1 divided by 9, which is that guy. Okay, and you get a nice partitioning. So next step here is that we should do a Monte Carlo integration with our Funder Corput sequence. So we go back to what we did in Monte Carlo integration, and you see here that we already created a Monte Carlo integrator, and that Monte Carlo integrator just takes as an argument here a random number generator. Well, but now it's not our interface, it is just this double supplier. Yeah. So this double supplier was also just an interface that has a method get as double. Yeah. So it was similar to our interface. So maybe I should have just used that interface from the beginning, but I also like to show you what you can do if you have this situation that you would like to be compatible with now this code, but you have here this interface random number generator. Because what you can just do is you can just say that this random number generator 1D also implements the double supplier interface. Okay, then the double supplier actually here has a different method, yeah, because it now requires that the method is not called get as next double. The method is called get as double. Yeah, so it has a different name. So in that case, what you can do is you can just add here a default implementation. Which tells me that this is just an alias to my method. Okay, so now all my random number generators just have to implement this method, and they will automatically have also that method, which we need here in our random number generator. Okay, so with this little modification, I can now use my random number generator together with my Monte Carlo integrator to calculate a Monte Carlo integral, but now not with a random number sequence generated by a pseudo random number generator, but now with the Funder Corput sequence. Okay, we still have to complete our implementation. Yeah, so I just created here this static method, but my random number generator should be an object that has state, so I can ask here the next double value. So let's add this state. So my state is first the base, and of course also some cursor like current index. Okay, that guy here can be final. Yeah, so it is set only once and then it is done. And that one here can be initialized to 0. So it is the initial index of this generator. So I need a constructor for these guys. So let's generate the constructor. Okay, the current index is already initialized. So I can now create here a Funder Corput sequence with a given base. And then if somebody calls the get next double, so give me the next random number, I just call here the get Funder Corput number static method with the base and the current index. And after that, I increase the index. Okay, so that's now my van der Corput random number generator. Maybe a small remark. We will later do experiments where we will, so maybe I have a session on multi-threading where we will do Monte Carlo in parallel. So there could be different tasks on different parts of the CPU that calculate with the same van der Corput sequence different parts of the integral. I already mentioned that here, for example, it's nice to use parallelization. If you like to parallelize by using the same van der Corput sequence object, that call here should be thread safe. And actually a small remark, this index plus plus is not thread safe. So it can be that one thread is incrementing it and then looking before he is looking at the value, the other thread is incrementing it and both see the value that has incremented by 2. If you like to make this thread safe, you have to take here something else, which is an object. So I can make it finer, and it is called atomic integer. So I can now create that guy. With an initial value, say, of 0. Okay, and then this atomic integer, this provides a method that has the name get and increment. So I have the same as the index plus plus, I get the index and then I increment it. But now this operation is atomic. Yeah. So if two concurrent parts are doing it, it is synchronized. Okay, that's just a subtle point, but now I have here a thread safe implementation of my get next double, because that method here is then called just with the corresponding arguments. So let's create a small Monte Carlo integration experiment. So here for my Monte Carlo integrator, there's nothing to do. I can just now reuse the old code. But now I would like to make a small experiment with you. Let's perform a Monte Carlo integration, for example, of the function x to the power of 3 on, just take here the interval from 0 to 1. So there's no transformation of the domain. I can immediately use my Mersenne-Twister random numbers and my van der Corput sequence random numbers. And I would like to do it with 3 different guys. First, let's consider a classical pseudo random number generator, for example, our Mersenne-Twister. Then consider this equipartitioning. So I could just take xi is I divided by n, or if I would like to make it even a bit better, I use the I plus 1/2 divided by n. Okay, so I is running here from 0 to n minus 1. And I would like to use a van der Corput sequence. Let's take a van der Corput sequence. And then I would like to calculate the integral error, where the integral, the analytic integral is clear. Yeah, so integrate from 0 to 1, x to the power of 3 dx is 1 divided by 4, x to the power of 4. And that's just 1 divided by 4, so 0.25. So I know the analytic integral. So I would like to compare the integration error, but now using different subsequences. Yeah, I would like to use here subsequences. Well, subsequences that have length m. So this means from this equipartitioning here, using a subsequence, then means that I take maybe these points that nicely fill the space, but then I stop. So this here is maybe now my xm, or if you start counting in 0, it's the xm minus 1. So actually doing this, yeah, just going from the left to the right, will create a fairly large integration error, especially for this function here, because this function has its highest variability, or the area where the stuff is going on, well, close to the point 1. Yeah, so you would expect that this guy here doesn't look so nice. Let's do this little experiment. So for this experiment, I need also the Mersenne twister. Well, we already used the Mersenne twister as a black box, but now if we have here this interface, of course, we could easily also create a Mersenne twister that implements here our interface. So maybe I do that because I need that also later. And then we do this experiment. So let's create a Mersenne twister that implements here our random number generator 1D interface. Okay, and well, I do not want to implement a Mersenne twister now from scratch. Yeah? So there are implementations of the Mersenne twister which you can use. Maybe I use one from a library. So there is the Apache Commons Math library, where you find a package called random, and inside this package random there is a Mersenne twister implementation. So let's create a Mersenne twister implementation from that library here. Create a constructor. Well, my constructor just takes the seed that should be used to initialize this Mersenne twister from this library here. Yeah? So I take now a new Mersenne twister from this library. Okay, then I can just use that guy, and whenever we call the get next double on our interface, I just route to the implementation in that library. So what I have created here is just a wrapper that is disguising this implementation from that other library to be compatible with my interface. So what I'm returning here is the Mersenne twister that we have defined, and they call it next double. So you see that their implementation also has a slightly different name, and I'm just creating this alias here, or this wrapper. So now I have a Mersenne twister implementation I can use here with my random number generator 1D interface. And since my interface is also a double supplier, we can use it with our Monte Carlo integration. So now this is an experiment on integration. Let's create then the class that should run this experiment here in the package integration 1D. And maybe I add the sub package called experiment. So this is now a Monte Carlo integration experiment. I would like to have a main method, and let's start a first experiment by calculating the integral for different number of sample points. So maybe I take here 10 million, or let's say 1 million sample points. So I would like to create the integral for a given number of sample points. So this here is the number of sample points. So first thing is I would like to integrate the function. So which function? So this is my double unitary operator. This is my integrand. So this is the function that maps x to the power of 3. And then I would like to integrate this function using, say, Mersenne twister. So now I have my interface, the random number generator 1D. So this is my new Mersenne. So this is now, I have to be careful, there are many now. This is now my own implementation here in this project. Well, and maybe I take a generator with a certain seed. And now I can use my Monte Carlo integrator, so the guy that we have created some while ago. So I have to provide the random number generator, the number of evaluation points, and then I can call integrate. So I call new Monte Carlo integrator. So it's that guy here with my Mersenne random number generator and our specified number of sample points. Okay. And you see, he's also fine, yeah, because he would expect here as an argument a double supplier, yeah, but my interface is also implementing the double supplier. So, well, you could now create here a new object, but I can also just call the new and immediately call a method on that object. And I would like to integrate now. So I would like to integrate my integrand from 0 to 1. So you remember here, this method integrate had as arguments the integrand, the lower bound, the upper bound. So that's just one line, and that's nice. So this is my integral with the Mersenne twister. Maybe let's print this out. Oh, and maybe let's run it. Here. So let's run it. Oh, what's that? Oh, sorry, that's a stupid mistake. Sorry, this method is just calling itself. Yeah. So actually here it should be get next double, right? So to create this alias here, I'm calling get next double. So this guy is calling this guy is calling that guy. So that was an infinity loop. He was always calling himself. Yeah. Okay, so we see with the Mersenne twister, instead of getting the 1/4, the 0.25, so which is my analytic solution here. Yeah. So instead of that, I get some numerical approximation. So maybe also print the approximation error. So let's print the approximation error. So let's have here the integral analytic, which is 0.25. So then I have Mersenne minus the analytic as the integration error. And we get a 10 to the -4. So 2 times, so actually something like a 10 to the -3. And we have here 1, 2, 3, 4, 5, 6. So this is a 10 to the 6. Yeah. So, and this is approximately a 1 divided by square root of n. Yeah? 1 divided by square root of n would be a 10 to the -3. So the nice thing is that we now can create with just a single line, yeah, or just 2 lines, a random number generator van der Corput by changing here on the right-hand side the van der Corput sequence. So this is now the new van der Corput sequence. So let's take van der Corput sequence with base 2. And I can just calculate here the integral van der Corput using now my Monte Carlo integrator with this other sequence. Yeah? All the other stuff, say the integrate is the same. Yeah? So I'm just constructing here a different integrator with a different sequence. Let's print that. So I print now the integral van der Corput and also the error to the van der Corput guy. And you see, I get a 10 to the minus 6. Yeah, so I get rather a 1 divided by n than a 1 divided by square root of n. You can also check this if you make this here now, say, this is a 10 to the 6, 2 times smaller, it's a 10 to the 4. So you get a 10 to the minus 4 here, but you get approximately a 10 to the minus 2 here. So you see, you have this nice feature that you can improve the accuracy by adding more and more numbers. It's an infinite sequence, and it's almost like 1 divided by n. So it is log n divided by n. Let's go back and do this here with the subsequences. So test the integral on subsequence. So what I like to do is I calculate the integral by adding more and more numbers. Yeah? So the feature that is so nice with the Monte Carlo method. So the Monte Carlo integral is the sum, summing up all the function valuations. So let's define here the sum. And I use a sum that uses the Mersenne twister. Then I use a sum that uses this equi-partitioning, yeah, the subsequence. So maybe I call it like that, subsequence of equi-distribution. And then I would like to calculate the sum, the running sum, with my van der Corput sequence. So let's do that for, well, we run from 0 to number of sample points. Okay, I smaller than number of sample points. So how many sample points do we take? Let's take, well, again, 1 million, maybe you can change that later. Okay, so now I calculate the partial integral with the Mersenne twister. So I add the function evaluation. So using my integrand, yeah, so I have to define my integrand. It's the same integrand, the x to the power of 3. I use the integrand. And now I evaluate that guy at the Mersenne random number. So let's create the random numbers generators. The first one is the random number generator that uses the Mersenne. So I can just copy these guys. Okay. The other one is the random number generator that has the van der Corput sequence. Okay. And the third one, maybe I do not need a random number generator for that because I can just calculate it. So let's evaluate the integrand at the first Mersenne random number. So take that into the sum, and then also do that for the van der Corput summation. Okay. And also do it for our equipartitioning. So in that case, I'm evaluating the integrand at, well, I'm evaluating it at I plus 0.5 divided by number of sample points, divided by n. So I'm going slowly from left to right. So now the integral is just that sum divided by the number of points. So the integral with Mersenne twistor is the sum. Well, divided by the number of points I used to approximate it. So that's not the number of sample points, that's the number of points I have used so far. So actually, I starts from 0. So if I have run the first time to this, I have used 1 point. So it's I plus 1. So we have now approximated the integral with I plus 1 points. So now let's do that for the other guys. Yeah. So I have an integral with this equipartitioning, and I have an integral with this van der Corput sequence. Oh, sorry, that should be this guy here. Okay, so I have these 3 integrals that use these 3 sums in their approximation. So this is now the sum, yeah, j from 0 to m minus 1 divided by m. Yeah. M is the part of the sequence. So this is now the approximation of the integral with a subsequence, and then the approximation quos and quos. So I can also add the analytic integral here, and we can now print the error for the different partial approximations. So let's first print the I. Okay, and then let's print the 3 approximation errors. Okay, these are 3 floating point numbers. So we can just use the G maybe. Okay, so I print now the 3 errors. So the first one is the integral with Mersenne minus the integral analytic. So that's the first approximation error I would like to see. Then maybe the equipartitioning guy, and maybe then the van der Corput guy. Okay, so I hope that is now a nice printout. Let's run that. Okay, so that runs now for a while, and unfortunately, yeah, it's not nice, yeah, because we see nothing here, because all the other stuff is already blown away here. So maybe not print every number, so only print if I plus 1, so that is the number of sample points we used, yeah, if I plus 1 can be divided, okay, that here is 1 million, okay, then let's print 100 numbers. So if the division by 100,000, 10,000 has no remainder. So that will print every 10,000 steps, yeah, it will do 1 printout. So and maybe here it's also good to print not the I, to print the I plus 1, yeah, because we used I plus 1 points. We started counting in 0. Okay, and now we see the following. So you see that here you have 1, 2, 3, 4, yeah. So you have a 10 to the minus 4 here approximately. So you see it for our van der Corput, the guy has an approximation error that looks like 1 divided by n. And in the end, we get also approximately the 10 to the minus 6 or 5. Yeah, so 1, 2, 3, 4, 5. You also see the square root of n convergence here. So this here is our Mersenne. The van der Corput is much better. Sometimes the Mersenne is quite good, yeah, but it is random. So you are adding more and more points, and sometimes the approximation wiggles around the true value and hits the true value by chance. So it can be that you are better, but it's random. In the end, the convergence looks like what we expect. But if you look at this equipartitioning, you have a huge approximation error for the whole steps, because the important part of the integral is in the last corner. And even here, if you just leave a few points out, the integration error is huge. But then in the final step where you have this nice structure, you get a very good approximation. So really the approximation relies on the fact that it's very structured, like in the Simpsons integral, where you had a very special structure of the points that generated a very good convergence rate. So you see that this advantage of adding more and more points, yeah, will give us a little bit worse approximation error compared to the equidistributed sampling. But for the equidistributed sampling, you cannot create this effect of just improving the integration error by adding more points. Okay, you find the code of this experiment again here in our GitHub repository. And maybe you can play a little bit with this, maybe also with different integration functions, yeah, or different parameters. And in the next session, I would like to discuss how we create now low discrepancy sequences in higher dimensions, because this was only the example for the one-dimensional case. And if you go back in our lecture, here with the Monte Carlo method, we had this little part that, well, from a one-dimensional sequence, I can easily generate a high-dimensional sequence by just populating the components. And this was also important in the Monte Carlo method being independent of the dimension, because every dimension is now an independent sampling, independent random number. But if you would use this trick with the van der Corput sequence, it will fail. And we will start with the coding experiment on that in the next session. And then we have to think that actually we have to create a new generator for higher dimensions. That was it for today. And sorry for being a bit over time.